Hey guys, welcome back to 14.6 reaction mechanisms. Reaction mechanisms basically take what we know about reactions and move it into a little deeper. Up to this point, we've talked about reactions happening in a single step, which is not true. They actually occur as several steps. So we write them as one long reaction, but it's actually several steps. So let's get to what a reaction mechanism is. A reaction mechanism is basically the steps that occur in a reaction. And so this is kind of like all the different steps that add up to be one whole reaction. And what all these steps are called elementary steps. And each step in a reaction mechanism, so it can't be broken down into simpler steps. Thus, the reason it's called elementary, because it cannot be broken down into simpler steps. So this is like one step of a multi-step process. Now, what that brings us to is the reaction intermediate. We saw in one of our above ones about a reaction intermediate, but a reaction intermediate is basically that one that we form in one step and then it gets used up in the next step. So that'll be important as we start writing these steps. So our rate laws for elementary steps, we have what is called molecularity. And molecularity tells us how many molecules are reacting. How many molecules are reacting? So if we have a unimolecular, that means we only have one molecule or one substance reacting. So that would be like maybe H2 breaking down into two H's. All right. And so our rate law is going to be just one thing here. So it's got to be first order with respect to that. Bimolecular means that we have, you guessed it, two molecules reacting. So we could think of an example like that. Let's just say H plus Cl going to HCl. I'm just trying to think of really simple ones. And so our rate law is rate equals K times the concentration of H times our concentration of Cl. And what we see here is that when we have elementary steps, we can write rate laws for them. And so we'll talk about that. Termolecular means we have three substances or three molecules hitting each other. All right. That doesn't happen very often because they have to occur with enough energy. They have to have the correct lineup. That's just not something that occurs at all. And so we don't usually see a rate law with rate times, let's just say A to the third. That just doesn't often happen. All right. And this is that key that I was kind of alluding to a few minutes ago. Although we cannot deduce the rate law for an overall chemical reaction from the balanced chemical equation, we can deduce the rate law from an elementary step. So if we have elementary steps, we can get the rate law. If not, we have to go from there. So that brings us to our next step. So we're talking about these individual reactions or individual steps. And so now we can talk about rate determining steps. And rate determining steps is the slow step. All right, if you're thinking of Thanksgiving dinner, the thing that occurs when Thanksgiving dinner happens is how long it takes the turkey to be done. All right, so that's what we talk about there. Our example there is, let's take a look at this reaction that's happening over multiple steps. We have this first one that has a very high E sub A, right? A very high energy of reaction or activation energy. And then we have the second one that's not as high of activation energy. So step one has a high activation energy. Step one has a smaller rate constant. Step one determines the overall rate law. So that determines how fast the reaction goes. So we have to see how it goes from there. All right. So our mechanisms must be valid and are only valid if the elementary step in the reaction mechanism must sum to the overall reaction. The rate law predicted by the mechanism must be consistent with the experimentally observed rate law. So there we go. So the problem is if we have a slow initial step, that's very easy to solve for. The problem is when we have a mechanism with a fast initial step. That's where the mechanisms with slow initial steps are easy to solve, like I just said. But if we have a fast initial step, our reactants, usually it's an equilibrium, and I know we haven't talked about equilibrium yet. That's where we're going next. All right, but we have an equilibrium. And so the rate of the forward reaction equals the rate of the reverse because the double-sided arrow tells us that we have both reactions occurring. And so then when we have equilibrium reached, the rate of the forward and the rate of the reverse are equal to each other. So we're assuming that we have an equilibrium, which is where the forward equals the reverse. So let's take a look at that. We're supposed to write a rate law for the following mechanism, and what is the overall reaction? So we have 2NO. Oh, missed our double-sided arrow, but we'll draw that in right now. Going to N2O2. And then we have H2 plus N2O2 going to H2O and N2O. And that's the slow step. And then we have N2O2 plus H2 gives us N2 and H2O. Now, the issue is our first step is we need to write our rate, or our overall reaction. So we're just going to put these guys together. And when we do that, what we can do is we can cancel out things that are alike on opposite sides. Like this N2O2, we can cancel out. And then we have another N2O2. Woo. Right there. And so it can cancel out as well. Alright. And so if we look here, I think that's all that we can cancel out. So we're going to get 2 NOs plus 2 H2s goes to N2 plus 2 H2O. So this is our overall reaction. So for our rate law to work, we have to have NO and H2 in it. But if we write our rate law for our slow reaction, which is just going to be K times the concentration of H2 times our concentration of N2O2. As you can see, N2O2 is not in our overall reaction, so we have to solve for that in some manner. And what we do know is that if we look at it, let's change our colors here just a little bit. So if we're looking at that first equation, if we write the rate law for it, rate equals K, and we're talking about in the forward direction, so rate equals K times the concentration of NO squared. We also know that equals the rate of the reverse, which is equal to K times the concentration of N2O2, because we're talking about an equilibrium. So we can set those equal to each other. Our K's cancel, our rates cancel, and so what we know is that the concentration of NO squared is equal to the concentration of N2O2. So now we can just plug this in for N2O2 up here. And so our rate is equal to K times our concentration of H2 times our concentration of NO squared. And this is our overall rate law based on our slow second step. All right, let's move on and finish this out. We're almost done here. Example 14.9, ozone naturally decomposes to oxygen by this reaction. 2 O3s goes to 3 O2s, and our rate law equals K times O3 squared times the concentration of O2 to the negative 1. All right, so we're showing that this proposed mechanism is consistent with the experimentally observed rate law. So we have to basically prove that this reaction or this rate law up here is equal to that. So the first thing that we should do is we should write our rate law for the slow step. All right, so we're going to write our rate law for the slow step. Rate equals K, and we're just, since it's an elementary reaction, we can just write our reactants times each other. If we were looking at this is a bimolecular because we have two reactants. All right, so we practice that as well. Now, what we see is that O is a reaction intermediate, so it cannot appear in our rate law, so we have to solve for O. So, switching colors again, back to red. Rate, if we're writing our rate law for our fast reaction, and in the forward direction, rate equals K times the concentration of O3. And the reverse reaction, which is equal to it, is K times O2 times the concentration of O. So that leaves us with O3 equals concentration of O2 times the concentration of O. So we have to isolate O because that's what we need to replace it with. So we're going to divide each side by the concentration of O2. And so that we know the concentration of O is equal to O3 over the concentration of O2. And so we can just plug this in right there, and that gives us K, and we're going to write it all out, O3 times the concentration of O3 over the concentration of O2, which is the same as rate equals K times the concentration of O3 squared times the concentration of O2 to the -1. Awesome. Thanks. See you next time.